Thank you. So, I tried to start from recalling yesterday. Is Ryan part of everyone? I want us to start from the recalling what we did yesterday. So, don't forget yesterday we discussed the regression line what? Y against X. I needed to talk. Regression line what? Y against X. And can somebody remind me why we focus on Y against X? Why not X against Y? What was the major thing that I mentioned? Yes, sir.
X is more accurate than Y.
X will be more accurate than Y. Why we have so much errors. So in situations where your X is more accurate than Y, I'll give you another context today, then you'll be able to understand what I mean by X is more accurate than Y. It is not so clear to you. Understood? Now, if X is more accurate than Y, it makes sense to substitute X to be able to get Y. So any error will lie on Y. Understood? And that is why we have to get a perfect line, we need to minimize that error. What is an error? It's a deviation from the actual and the estimate. Am I making sense? The deviation from the actual and the estimate. Oh, I'm guessing Jensen can run from here to here within 5 seconds. That's my estimate. If Jensen eventually runs in 3 seconds, then there's an error gap of 2. There's an error. Do you understand that?
Yeah.
Okay, so an error is actually the deviation, the difference, the gap between the actual and the estimate. So when you substitute any x, y, z, any x1, x2, x3 into the line, you get the actual because it's on the line. However, that's not the point that you have. Well, I think the table is actually the actual. x1, y1, x2, y2, you have that in the table. But that is not necessarily on the line for the x values. So this is another demonstration just like yesterday. You have x1, y1, x2, y2. These are the actual values. Oh, time spent on social media, great. Time spent on social media, great. Those are the actual scenarios. But after collecting data from 1,000 students, we came up with a line. So it means for these two, there are gaps. These are the errors. Okay? And the error, the model will be perfect if we can have the least error. When I was going home yesterday, it occurred to me that I watched, with all this racial thing going on in America especially, so there was another documentary that came to light, a guy that was convicted because the software recognition says the criminal matched his face. And he was sent to jail, I think, for like 10 months. But the problem with that is now that when you take your passport, this is your face, take your picture now, and you bring the picture of the guy that is being looked for. After all, there's a picture. You can see with naked eyes that they are not the same people. It means somebody behind that program has not considered the least possible error when generating that model responsible for the code. Because it has to be as perfect as possible. You're going to be ruining people's lives if it is not. Do you understand that? If the software is about your biometrics, if it doesn't work, it means when you're registering, it says, oh, I see your face, I see your hand, and suddenly, you need to quickly take your phone and call your parent for something, and you put your hand, it doesn't recognize, you put your face, it doesn't recognize, oh my God, and then something happens. Because behind all these codes, behind all this program, there are regression models there. There are regression analysis going on behind the screen. Just Google machine learning. One of the key things you must be very proficient in is your regression model, regression analysis. It has to be a perfect fit. That's the reason we are teaching you some of this stuff. Of course, we're not going to teach you how to make a software here, but at least we can introduce you to the world of correlation and regression. Then some other professionals will build on it in some lab, somewhere in China, somewhere in Australia, and you won't look like a novice that, oh, I never had a regression before. Do you understand the idea? So error, minimizing error is very important. We're not saying it has to be 100% perfect. No software is ever perfect. But the error must be minimized because life could be ruined. My guess is the officer behind, whatever, the program, running the program, might not be racist. He might be scanning 1,000 cases. And anyone that says 99% match, just send the automatic email to the boss, arrest this guy. Without actually looking at it manually, because maybe there are so many cases they are dealing with. But then the news was actually, I think, focusing on the prosecutor. Even when the officer's software says this is the guy, you have eyes. Could you at least check and say, oh, but that doesn't look like Joey? Do you get the point? And that was why it made the news. Because normally it shouldn't make the news. As a lawyer, I should say, oh, sorry, I think these are one of the error cases in the software. This is not the guy we are looking for. And I think it's been 10 months for nothing because of things like this. Okay? So any inputs should be correctly measured to minimize the errors in the output. Because by the time you compute your A and B using that, okay, you know how to get the coefficient, don't worry. By the time you compute your A and B, remember, how many signal figures did I just say you leave your answer to? 3. How many do you see in your calculator? A lot. And then you're focusing on 3. Let's do something. Everyone. Joey, come here. Like here. Everyone, put this in your calculator. Raised to power, let's say, 99. Then do this also. Also raised to power 99. Tell me what you notice.
A lot different.
By lot, you mean?
Wow.
Don't show me. Tell me. Okay, what is this one?
2.67.
2.67. What is this one?
48.46.
Can you see that? 48.56. Can you see that? Even though this might be 0.1247 something, this might be 0.41 something, it eventually you'll be like, 3 is not figure, I'm just going to pick this one. Okay? Or better still, maybe there is a number such that when you round both of them in different scenarios, maybe to 1 signal figure or maybe to 2 signal figure, you have, let's leave this as this. Somebody say 1 decimal place and somebody say 2 decimal places. The same number. Can you check what this will be? That will be 1. Agree?
Yeah.
The same number. And you get 48. Can you see that? So the error may not be noticeable in that situation, but when applied in something else, it becomes a big deal. Just like when someone was writing that code, facial recognition code, the error may be a minor thing. Is that not? But eventually, when they send somebody to jail for 10 months, it becomes a big deal. That is why we must ensure that our input is as accurate as possible and be able to minimize the output error. Does this make sense? So, that was yesterday. Because our input will be as accurate as possible in that scenario, we try to minimize this, and then our focus is on having a least square from the deviation on the vertical measures. Okay? And then we came up with some formula yesterday. But for today, in some scenarios, the error will be on your x. Remember, when you have your line y is equal to ax plus b, if somebody gives you x, you should be able to get y. If somebody gives y, you should be able to get x by making something the subject. Is that not? So in this case, you realize that, oh, actually, x has error, y is more reliable. And I've given an example there, I think here. Look at the social media thing and the performance, for example. The number of times you spent on social media you can't really measure that. But your performance, because we have a valid description, oh, you got a 2, oh, you got a 7. But you cannot say, oh, I spent 37.12975 seconds on social media. Do you get the idea? So there will be more errors on that social media, time spent on social media, while your performance can be more reliably measured. And if you look at it, the social media one should be the independent variable.
Yes.
While the performance should be depending on that. Am I making sense?
Yeah.
So your performance is the Y. The time on social media should be the X. This time around, your X is the one that is not as accurately measured as possible.
Yeah.
Are you with me? So in that situation, you focus on, okay, let's have a regression line so that I don't have to substitute something that is not reliably measured. Let's have the regression line the other way around. And that is this type of regression line. X, I'm not using A and B anymore. My plus n. So that when we substitute something that is more accurate, then we can get this one. And when someone is interested in Y, we can substitute X and make Y the subject. As long as the relation that generated the model is based on substituting something that is more accurately measured. That's the idea of having regression X on Y, regression Y on X. Does that make sense? So in some question that will be challenging, you'll be given a scenario, then you'll be charged with the responsibility of identifying whether to use X against Y or Y against X. It's easy to identify the independent and dependent variable. Then you will think about it yourself. Which one is more reliably measured? Which of the data could have been an approximation and not exact? And that determines whether to use X against Y or Y against X. There are some questions like that in the next worksheet. Some of them IB questions, some of them just from your textbook. Understand? So I'm giving you this context, the criminal justice and everything, so you can understand. Then please don't just solve question because, oh, there's a calculator, Mr. Daniel said press this button and that's it. No. Put yourself in that situation. See yourself as that somebody that works with innocent project, trying to exonerate that man that was sent to jail unnecessarily. Because that is how this thing works in real life, dude. That's how it works. Those folks just, do what they want sometimes. Then you come in and say, oh, I'm a scientist, I do this. I think I was telling you guys about refractive index and things like that recently. I saw it on the board and I'm like, wait, do you guys know they use this in forensic science? I've seen tens of documentaries where, okay, let me give you a context. So there's one, somebody robbed somebody, or maybe this somebody, maybe somebody died eventually, and they have to look for the criminal. So maybe they try to find DNA. I'm sure you know we leave DNA everywhere we go, right? I think they couldn't find DNA or something. Then they use, or maybe after getting DNA, they are looking for more. They have to be able to prove beyond reasonable doubt, right? That's the term, beyond reasonable doubt. So which means if you give one evidence, it's not enough. But you can give 5 different or 10 different evidence. Well, actually, we see that Kelly's, sorry, I used Kelly. Kelly's phone, when we make a call, I learned over the years that when you make a call, the cell tower around that neighborhood connects to your phone, right? So that also leaves digital footprint. So if you claim that, oh, you are not responsible for what happened, how come your phone connects with that cell tower in that region? But that does not mean that you are the one guilty of the crime. It's just one. Your sister could have taken your phone. Somebody could have stolen your phone and was passing through the whatever, right? So that is why they need more evidence. Another evidence could be, okay, we saw a can on the street and we tested it for DNA and it matches your DNA. Oh, the criminal could lie and say, okay, I threw it somewhere in Taipa. Maybe the people who cleared the rubbish took it to Kolowan. It doesn't mean I was in Kolowan. All right? Then, okay, in the house of the criminal, a glass was broken. And in your car, we found a glass as well, where it could have been any other glass. So what they do is to test the refractive index of the glass at the crime scene and the glass that was found maybe on the jacket of that person or maybe on the shoe. Like, dude, you're carrying this around everywhere you go. This is not somebody planted the evidence anymore. Oh, we found it with you. And they were able to check the refractive index. I can't remember how many different documentaries that was one of the evidences that was presented in the court. So these things are not just calculate. Some people are using them for real life situations. Just find FBI files on YouTube, forensic science, FBI files. You'll be amazed how they solve, crime-related problems with science, maths, technology, even arts. You'll be surprised. And if anyone is interested, look for this movie Numbers. Number with E as 3. Numbers, N-U-M-B-3-R-S. I was crazy about those films in the early 2000s. Every episode is different crime-related stuff and different mathematical whatever that I don't even understand. I'll try to find one episode, and maybe one of these classes I'll play one for you. We just watch Numbers, So my point is, see the question you are solving beyond just pressing calculator and writing conclusion. Put yourself in that situation. See yourself as that person solving the problem in real life, and it becomes clearer to you. Okay? So, quickly here, this is from yesterday. I just want you to see the difference. This is from yesterday. This was what we proved. Okay? For the x and y, if we put it in this form, the coefficient is similar to this, except that the denominator is in terms of y. Again, you don't need to memorize. The only thing you are going to change in your calculator, after you put the data, when you go to your lists, you change list 1 to the first one, you interchange list 1 and list 2. And every other thing remains the same. Okay? So your coefficient is that. And again, this will just change positions. So instead of y bar, you have x bar. Instead of x bar, you're going to have y bar. And a is what you have found already. Just like m is what you have found already. Again, no need to memorize this. This is just for information. And anyone who wishes, consider the horizontal distance like I've shown in that diagram and see if you can prove this. Similarly, just like we did yesterday. Okay? Just if you want to just, try something out on your own. Okay? It's doable. Just like we did yesterday. Exactly follow the process. But this time around, you're considering horizontal distance. Okay? And you can call it D1, D2 or something as well. Now, let's see. When you plot your x on y and y on x, they are not going to be the same. And we can see that from here. Maybe I call that observation. Let's look at the board now. So let's look at the following observations. We know that the regression, I'll stick to my blue or black. Okay, regression line, x on y, okay, no need to write all that. From here, okay, from x equals to my plus n, let's see what happens if we make y the subject and try to compare with the first one. We could see clearly that x minus n is equal to my, which implies that y will be equal to 1 over mx, right? Minus n over m. Do you agree?
Yes.
Carolina? Talk to me, please. Yes or no? That's all I want to hear. Yes or no? Talk.
Yes.
Anika? Yes? Okay. So you just divide by n, right? Now, let's compare with y is equal to ax plus b. Does it mean a is equal to 1 over m? Compare with 1 over that. So my question, does it mean a equals 1 over m and b equals minus n over m? That's the question. Does it? Yes or no, you have to tell me with a proof. Beyond reasonable doubt. Anyone? Don't press calculator. Don't press calculator. This is the reasoning stuff. Because the idea is I want to see whether the two lines are actually the same or not. So if the two lines are the same, it means that when you make this the subject, you should be able to get the same thing again. So that's my question now. Yes, sir?
No,
Why?
because when A is the formula and you flip that around, it's not 1 over m.
Can you give him a round of applause? That's it. Please, come on. If you look at it, look at your A here. 1 over m means when you flip this around, do you get the same thing? No. And look at your B. Minus n over m. Look at your B here. There is no way negative this divided by this gives you the same thing as that. So this is an evidence that regression line x on y and y on x are not the same. But they meet somewhere. Can somebody guess where they meet? I can't hear that. What? The midpoint. Why do you think they will meet on the midpoint? That's correct. They meet at the midpoint. Please appreciate that for that. They meet at the midpoint. But why? Why? We have said something at the beginning, I think yesterday or the class before. Every regression line passed through the... Was there any specification or restriction? We never said x against y, y against x. We never. The only reason why we are discussing x against y, y against x is the reliability of either x or y that is given. That was never a factor at the beginning. So where they meet is your mean point. Does that make sense? You need to remember this fact that we just analyzed because it came out in numerous IB questions that I've seen. In fact, one of them was part of the mock question that I gave the Form 6, either part of the mock or one of their final tests. The question will tell you, okay, find regression line x on y. Then another question, find regression line y on x. Then you see something like, the two lines meet at point P, Q. Find P and Q. So don't start solving simultaneous equation. That's a waste of time. So you know your P, Q is the main point. Just go back to your table. Find your x bar, find your y bar, and that's your P and Q. Does that make sense? Okay, so they are not the same. That's the last conclusion I'm going to write. And they will meet at the main point. Okay, so ladies and gentlemen, let's try to, I will show you the regression line x on y. So let's try this. So go to your calculator now, everybody. Go to your calculator now. Put this information in the calculator. Let's make it bigger. Just to test how to find the regression line x on y.
So which one do you put?
This information you can see.
What's your book?
What?
So they're like one graph.
This one. There's no space, clearly. Quickly, please. This is continuation. There's no space. It says 12 chickens, right? And that's not 12 if you don't combine the two. So quickly, let's be serious and focus, please. Are you there yet? Once you do that, find your regression line the way you have done before. Nika, what's going on? You don't have a calculator? What? Okay. Oh, I have Elson's battery, by the way. This dude said he bought the battery for your calculator.
Oh, he did? Oh.
And he was so happy. Oh, that's so kind and considerate of him. Like you even remember. You want to give him extra battery. So thank you. Okay, are we there yet? Please, quickly. All right. Now, do your regression line the way you have done before. Don't change anything. And tell me if it is the same as this A and B. Is it the same?
No.
No. But this is about X and Y. So now what you are going to do is to change the list. Go to where you change the list. Where do you change the list, Ada? You're wasting my time. Go to where you change the list. Now X list, change it to 2. Y list, change it to 1. Now do everything the same way. Continue. And tell me if you see this.
How do you switch them?
Yes.
How do you switch them?
Jensen, how do you switch them? Be careful with the camera.
Go to.
Did you get this? X list, change your X list to 2. Just follow my instruction, don't type what you can see. Change your X list to list 2 and Y list to list 1.
I got you.
No.
Change that to 2. And change the next one to 1. Then continue. And when you continue, don't do regression. There is something on the screen. Go back. Don't take the regression A plus BX. You continue with your AX plus B.
Oh, I did it.
Okay? Did you get this? That's how you find your regression line X and Y. You just change the list.
Switch these two.
So basically what you are saying is that your list 1 is supposed to be your reliably measured figure. So you are just switching it. Once you switch it, that is the command to tell the calculator, okay, this new stuff is my regression line X and Y. Please, once you do that, please go to your seat. And you must be able to find your way back. So if the question is about X on Y, you have your list interchange. If the question is about Y on X, you need to have your X as list 1, Y as list 2. Am I making sense, please? Carolina, what is going on? Are you still doing this?
I'm not getting it.
You're not getting it? Speak to someone close to you and stop wasting time. Melody, done?
Nothing changes though, switch it back.
Do not pick A plus BX. Pick AX plus B. I said everything should be the same. The only difference then is change the list X to list 2, Y to list 1. Every other thing that you press on your calculator should be the same. Mr. Texas Instrument.
Got it.
Okay, great.
There's L1 and L2. This is quickly.
Quickly, please, quickly. You have 30 more seconds to figure that out and go back to your seat.
Yeah.
No. Yeah, okay. Thank you.
Switching backwards.
You guys are
Wait,
fine.
you went into the graph and then you did it?
The graph.
It didn't work.
How did you get
6.
Wait, Jensen.
Graph 1. Calculate.
I see, okay.